Let me ask you something. What do you think gravity is? Go ahead, take your best guess. You probably said something like gravity is a force that pulls things together. Or maybe gravity is what keeps your feet on the ground, what holds the moon in orbit, what stops the atmosphere from escaping into space. Or maybe you're a little more sophisticated and you said gravity is a field, like the electromagnetic field, a force that acts across distances between masses. Here's the thing, every single one of those answers is wrong, or at least so fundamentally incomplete that getting them right should genuinely disturb you. I'm Leonard Susskind, and I have spent decades thinking about gravity, decades, and I can tell you with complete honesty that gravity is the strangest force in the entire universe, stranger than electromagnetism, stranger than the nuclear forces, stranger than quantum mechanics itself in some ways, because gravity is the one thing that connects all of those mysteries together. And more than that, gravity is the one force that might not be a force at all. So buckle up. We're going to take apart everything you think you know about gravity piece by piece and put it back together in a way that's actually true. Let's start with the most basic misconception. Most people think gravity pulls. They think it reaches out across space, grabs hold of things, and drags them together. And on the surface, that seems obviously correct. Drop a ball and it falls. The moon orbits the Earth orbits the sun. So clearly gravity is pulling, right? Except that's not what's happening. Not even close. Here's what I mean. Newton gave us an extraordinarily successful description of gravity, a mathematical formula that predicted the motion of planets, the trajectory of cannonballs, the behavior of tides. Newton's law of universal gravitation worked so well for so long that people forgot it was a description, not an explanation. Newton himself knew this. He famously said he would feign no hypothesis about what gravity actually was. He could calculate it. He couldn't explain it. It took Einstein 230 years later to finally explain it. And the explanation is one of the most beautiful and deeply strange ideas in the history of human thought. Gravity is not a force, it's geometry. Let me explain what I mean by that. Einstein's general relativity tells us that space and time are not a fixed background against which physics happens. Space and time are themselves physical things. They can bend, they can curve, they can warp. And mass, any mass, causes space-time to curve around it. The Earth curves the space-time around it. The sun curves space-time even more dramatically. A black hole curves space-time so severely that not even light can escape. And here's the key insight. When objects move through curved space-time, they follow the straightest possible paths through that curved geometry. These paths are called geodesics. And what looks to us like a curved trajectory, like a ball falling toward the Earth or the moon orbiting the Earth, is actually the straightest possible path through curved space-time. The ball isn't being pulled down, it's following a straight line through a curved geometry. And because the geometry near the Earth curves toward the Earth's center, the straightest path happens to lead downward. Gravity isn't pulling you toward the Earth is curving the space-time around it, and you're following the natural geometry of that curved space. Now, I know what you're thinking. That sounds like philosophy, not physics. How is curved geometry different from a force? What's the actual difference? And this is where the experiment comes in. Because there is a profound, measurable, observable difference between a real force and gravity. And Einstein identified it in a thought experiment that he called the happiest thought of his life. Imagine you're in a box, an elevator, floating in empty space far from any gravitational source. You're weightless. Everything floats. Now imagine someone accelerates that elevator upward at exactly the right rate. Suddenly you feel weight. Objects fall to the floor. Everything behaves exactly as if you're standing on the surface of the Earth. Einstein's insight was that these two situations are physically identical. Not just similar, identical. There's no experiment you can do inside the box that will tell you whether you're in a gravitational field or accelerating through empty space. This is the equivalence principle, and it has a consequence that is genuinely shocking. If gravity and acceleration are physically identical, then gravity is not a force in the conventional sense. Real forces like pushing or electromagnetic forces can be detected by accelerometers. They change your velocity. They push you. Gravity doesn't. In free fall, you feel nothing. Weightlessness. An astronaut in orbit is in free fall. They feel no gravity, not because gravity isn't there, but because they're following the natural geometry of curved space-time. The force is zero. The geodesic is everything. But let me take you somewhere even stranger, because this is where general relativity starts to genuinely break your intuitions about what the universe is. If gravity is geometry, if it's the shape of space-time rather than a force acting through space-time, then massive objects don't attract each other. They change each other's geometry. The sun doesn't reach out and grab the Earth. The sun warps the space-time around it, and the Earth follows the geometry of that warped space. And here's what makes that deeply weird. The geometry changes in time as well as space. Space-time, not just space. So when the sun's geometry changes, when it moves or oscillates, those changes propagate outward through space-time at the speed of light. Ripples in geometry, gravitational waves. In 2015, a century after Einstein predicted them, LIGO detected gravitational waves from two merging black holes a billion light years away. The entire Earth contracted and expanded by less than 1,000th the diameter of a proton as those waves passed through us. The geometry of space-time itself was oscillating, and we felt it. Think about what that means. Gravity is not a signal sent through space. Gravity is the shape of space, and we can detect the universe changing shape around us. Now let me tell you the deepest problem, the one that should keep every physicist awake at night, the one that has certainly kept me awake. We have two extraordinarily successful theories of physics. General relativity, which describes gravity as geometry, which works perfectly on large scales for planets, stars, galaxies, the entire universe, and quantum mechanics, which describes everything else, electromagnetism, the nuclear forces, matter itself, which works perfectly on small scales for atoms, particles, and quantum fields. And these two theories are fundamentally incompatible. They contradict each other at the deepest level. General relativity assumes space-time is smooth, continuous, and classical. Quantum mechanics says everything, including space-time, should be quantized, fuzzy, probabilistic. You can't have both be exactly right. At some scale, one or both must break down. And we know where they break down, inside black holes at the singularity where quantum effects and gravitational effects become equally important, and at the Big Bang, where the entire observable universe was compressed to a point of infinite density. At those places, both theories give nonsensical answers, infinities, breakdowns. The mathematics waves a white flag. The unification of gravity with quantum mechanics is the single greatest unsolved problem in theoretical physics. String theory is one attempt. Loop quantum gravity is another. But we don't have the answer yet, and the core of the problem is this. Gravity, unlike every other force, is geometry. Every other force, electromagnetism, the strong force, the weak force, they're all quantum mechanical. They're carried by particles, photons, gluons, W and Z bosons. They fit naturally into the framework of quantum mechanics. But geometry, curved space-time, how do you quantize the shape of space itself? How do you make space-time fuzzy and probabilistic without destroying the very framework that makes physics possible? These are the questions I've spent my career on. And I can tell you with complete honesty, we're closer than we were. The holographic principles, string theory, the ADS-CFT correspondence, these are genuine insights into the quantum nature of gravity. But we're not there yet. The full picture remains out of reach. Let me bring this back to something you can feel. You are sitting right now, feeling your weight in your chair. And what you're feeling is not a force pulling you down. What you're feeling is the floor pushing you up, the normal force from the surface beneath you. The earth is not pulling you. The earth is curving the space-time around it, and your natural trajectory through that curved geometry would be to fall toward the center of the earth. The floor is preventing you from following that trajectory. The floor is applying a real upward force, and that upward force is what you feel as weight. In the deepest sense, you're not being pulled down by gravity. You're being pushed up by the floor, and if the floor weren't there, you would feel weightless, falling freely, following the geometry. That's gravity, not a pull, a shape, not a force, a curvature, not something reaching across space, something that is space. And here's what I find most profound about all of this. Gravity connects everything in the universe. Every mass, every energy, every bit of information curves the space-time around it. Every curve affects everything else. The universe is one vast, interconnected, dynamic geometry, constantly changing, constantly evolving, from the quantum fluctuations at the Planck scale to the large-scale laws, the structure of galaxies and cosmic filaments, and all of it, every bit of that geometric dance is what we call gravity. Not a force, a conversation between matter and geometry. Matter tells space-time how to curve. Space-time tells matter how to move. And that back and forth, that mutual influence between mass and geometry is the deepest description we have of why things fall, why planets orbit, why light bends around stars, why black holes exist, and why the universe is the shape it is. So the next time you drop something and watch it fall, remember, it's not being pulled. It's following the shape of the universe. And that shape is one of the most beautiful, mysterious, and still incompletely understood things in all of physics. Gravity is not a force. And understanding why might be the last great revolution in our picture of how the universe works. Thank you for listening. Now go stand somewhere and feel the floor pushing up against your feet. And remember that what you're feeling is not gravity pulling you down. It's the universe holding its shape. And you, right now, are bending it